Good morning, everyone. Okay, so about 76 of you are here. It's about 75%. All right, so we can get started. Okay, so good morning once again. My name is Mr. Ravi. So I'll be your lecturer, okay, and module coordinator for this CG2271 real-time operating systems. Okay, so most of you know me for EPP1 and EPP2. Okay, so I should be a familiar face to most of you. Okay, so unless maybe some of you may be from other departments who are taking this module as one of your electives or things like that. All right, so then maybe you're seeing me for the first time. Okay, so in today's lecture, we're going to go through some important matters about the course, how it's structured, okay, the deliverables, okay, what you need to do within this week and next week, all right, and what is important to get you started, all right. So it's good that most of you are here, all right, so hope the rest join in soon. So we have about 100, 102 students registered, all right, so you should stabilize by this week, all right, and these numbers are a bit higher than last semester. Okay, so we also need to make some adjustments for that, all right, which I will talk about later on, all right, for the lab. Okay, so again, welcome to this module. Okay, and let me get started, okay, by sharing my screen over here. Okay, can everyone see my screen? Yes.
Yeah, I can see.
Thank you. Okay. Okay, so let's get started, all right, with the course overview, all right, to better understand what we are here for. All right, so first about me, all right, so again, my name is Mr. Ravi, all right, this is my office at Com2. Again, ever since we were hit with COVID, I only go back once a while, all right, so for now, I go back Tuesdays, Thursdays, and Fridays, all right, so other days I work from home, all right, so I think it's still easier if you just directly contact me, all right, so the easiest way is, of course, all my students have my handphone number, so you can directly WhatsApp me, all right, if you need to ask any clarification about anything, all right, but of course, for a simple clarification, it's easy, WhatsApp, I can just reply to you. Okay, so it's something that is more lengthy, more detailed discussion is needed, then you can probably email me, okay, your question, and then we can discuss it through email. Okay, yeah, so I think that is still the easiest way. Either WhatsApp me directly or you just email me. Generally, my research is in the area of embedded systems, robotics, mechatronics, and things like that. All right, and before switching to academics, previously I was with Hewlett Packard Singapore, okay, working as an R&D embedded software engineer. All right, these are my profile links. All right, so if you wish to again just keep in touch even beyond the module, you can always follow me on those pages there. All right, yeah, so along the way, a few things. If you want to ask any questions, feel free to either put it in the chat, all right, or unmute your mic and ask me. Okay, at the same time, if I get disconnected at any point of time, all right, due to any Wi-Fi issues or things like that, just stay in the Zoom call, all right. I will join back in and then we can carry on. Okay, if for some reason suddenly you can't hear me, okay, you can't see the screen and something is wrong, all right, just feel free to give me a call and let me know that something is wrong on my side, all right, so then maybe I can check what's happening. All right, so this is just to make sure that our classes run smoothly. All right, so these are the teaching assistants that we have for all of you. Okay, so we have 5 of them, all right, that will be there for the, sorry, 6 of them for the labs. All right, Wamika, Daniel, Praveen, Khairul, and Vishruti and Kaiwan. All right, so Kaiwan will also be doing the tutorial, all right, and then Yuhang. So all of these tutors here, okay, majority of them have had experience with 2271 before, so they are well versed with the curriculum and the structure and how it is conducted. All right, so I'm sure they will do a good job, all right, in helping you through this module. Okay, so you'll get to see them in your tutorials and in your labs. All right, so in terms of lectures, we have basically about 12 weeks of lectures, all right, 2 hours a week. Tutorials, we have 9 of them, all right. Labs, we have 8 labs plus 1 project, all right. And this is the overall assessment. Okay, so this assessment is again, if there are any changes, I'll update you. But for now, this is the plan, all right, where you have a final exam 40%, you have a midterm, all right, which is 15%. Lab attendance and demo is 5%, and your project is another 40%. All right, so as you can see, your project is quite a heavy weightage. At the same time, your exam is also equally weighted. All right, and why I say this upfront is because sometimes your project you may do very well, all right, and your whole team gets a good score, all right, but then your final exam maybe you did not do as well, all right. Then you will see that, hey, how come my friend in the same group, he got an A, I got a B plus? You know, is there something that went wrong? Okay, so these are things that are quite normal. Okay, so even though in the same project group, okay, your team does very well, all right, doesn't mean that everybody is going to end up with the same grade, all right, because you still have your final exam, which is 40%, your midterm, which is another 15%. So that still plays a part, and that is individual. All right, so just because you do well in the project, all right, that is still not enough. We still need to make sure you do consistently well in the exam and in the midterm as well. Okay, then you can sort of aim for a good grade. Okay, so in terms of the exam, okay, when is your final exam? All right, so just to be sure, okay, I think ever since we switched to Luminous, Luminous always updates the exam schedule. So you can see down here on your Luminous page, once you log in, it will show you the exam schedule. All right, so it is currently set as 28 April, okay, 9 to 11. Okay, so you can probably check across all your modules as well, okay, just to be sure you have all the dates correctly. All right, so just remember the date, okay, for your final exam. Okay. Okay, so this is the detailed schedule. All right, so your batch is probably the first batch that is in a way impacted in a not so good way because of what is happening in week 13. Okay, week 13 Friday is Good Friday. All right, so normally what happens is I always push the project assessment all the way to the end. All right, but because it is a public holiday and there are no classes, all right, we can't have it, so we have to push your assessment 1 week earlier. All right, so this is something you have to take note of. Okay, your assessment is not going to be in week 13, it's going to be in week 12. All right, so this is a very important change, all right, compared to previous batches here. 1 week your assessment is 1 week earlier. All right, so of course, because of that, I also tried to make some adjustments on my side to cut down some of the earlier material a bit so that we can start the OS part earlier, okay, and cover through. All right, so this is again a rough schedule. All right, in terms of the actual flow, we will again make some adjustments as and when needed. All right, so another important week is your week 4, all right, where you have your Chinese New Year week. All right, so we don't have any scheduled lecture and tutorial for that week, okay, but labs are still ongoing. All right, so just take note of that for week 4, okay, the Chinese New Year week. All right, yeah, so anyway, weekly I will still send updates just to remind us on what we need to cover for that week. All right, and the project assessment, again, this is important, week 12. Okay, all your robots will have to be submitted at the start of your lab session. Okay, that means you do not consider week 12 as also a day for you to work on your project. You don't have time to work on your project on the Friday of week 12. All right, when you come to lab on the Friday of week 12, If you are 10 a.m. slot, you surrender your robot at 10 a.m. If you are 2 p.m. slot, you surrender your robot at 2 p.m. Okay, so you really don't have time to work on anything in week 12 itself. Okay, so everything has to be done earlier. All right, so you need to plan your schedule, okay, within your team. Okay, try to maximize your lab time and get things done earlier. Okay, and make sure you have everything ready by week 12. Okay, so what is the curriculum? All right, so before I took over this module, which was about 3 years ago, all right, it was quite different. Okay, I mean, I basically they were using Arduino Uno, and the only fun part of the lab was you see LEDs blinking. All right, so I think that is really not adequate for what is expected of a computer engineer. All right, to say that they have learned RTOS. All right, so I revamped it totally. All right, to cover a lot of very important things, which I think are important for you as a computer engineer, and also to extend your knowledge beyond what was being taught in the past. All right, so there are a lot of new stuff. It is still evolving. All right, in fact, last semester I also introduced something new, which I'll talk about later. In fact, for your batch also I was planning something else, but I didn't have time to finalize it. All right, I don't know whether it's good or bad, but I'll tell you about that idea a bit later. All right, so in terms of the reviews of this module, I think you can just go directly to NES Mods to have a look. Okay, I think that sort of gives you a good idea of how your seniors have viewed this module, especially with the changes. So so far I think it's good. We're heading in the right direction. All right, and along the way, I'm always looking out for opportunities to make this even better. Okay, there is no particular reference text that you need. Okay, all the required material will be provided, and there are also lots of reference material and hardware software solutions online. Okay, so you don't need to borrow any book or buy any book, okay, as a reference text. Okay, tutorials will start from week 3. Okay, so as of now, it is still scheduled to be online through Zoom. All right, so your tutors will send you all the Zoom links, okay, for you all to attend. All right, so as much as possible, try to go through the question, all right, and try to think of the questions you want to ask. I mean, even if you don't solve it, okay, but at least you think through and have an idea of what this question is about. Okay, what is the concept? So when it is being discussed in the tutorial, you can ask some questions to clarify your doubts. Correct. If you come to the tutorial and you see the question for the first time, you may not know what to ask. Correct. So I think the whole idea of tutorial is not to check whether you have done the work. It's more of an opportunity for you to ask questions to reinforce that learning. Correct. So if you don't do the questions, at least have a look at it, to have some idea of what we are discussing. All right, what do you think is the answer, and then you can have some maybe meaningful session during the tutorial class. All right, I've asked the tutors to do a video recording, okay, through the Zoom. So in case they forget, just remind them. All right, so they're supposed to do a video recording, and I send you all the recording link at the end of the tutorial. Okay, so so this one of the major changes, okay, like I mentioned, is we have switched away from the Arduino Uno platform to bring you the ARM Cortex-M0 Plus processor over here. So it's a very powerful board. All right, very exciting. It has very wonderful features. All right, so even though we only are going to touch a bare minimum of it in this module, all right, you can really learn a lot of it, okay, as you explore it further. All right, so that is one of the most exciting changes, I would say. So you need to form a lab or project group, 3 or 4 per team, preferably 4. Okay, so I think it's more easier to divide the work with more of you all. And I'll talk about the lab registration a bit later. Then certain labs have demo requirements. All right, so I would say not certain labs. Basically, there's only one lab. Okay, there's only one lab. I'll show you where you need to demonstrate some functionality. And the reason why I put that as compulsory is to make sure that some critical parts of the project are already done till then. All right. So the way the labs are structured. Okay. So if you look back here at the schedule, okay, this lab file here. So this is the lab demo. All right. And why is this lab demo important? Because up till then we are doing all the low-level device driver development. All right. And as you can see, what we are trying to do is we have structured the lab such that you progressively build up the robot. Okay, we talk about the LED interfacing, the interrupts, the PWM, the timers, and so on. So when you come to lab 5, you should be able to send a command to your robot to make it perform some action. All right, by controlling the motors and controlling the LEDs or things like that. Okay, and that is an important part because that ensures that all these low-level device drivers are in place. So when you start the RTOS labs, okay, after the break, it is more of integrating the RTOS architecture, okay, to fulfill the project requirements using the device drivers you already developed in the first half of the labs. All right, so that is why I structured this lab demo, okay, to be compulsory so that everybody ensures, or we can be sure that everybody has reached a certain milestone before we cross over to the OS part. Okay, yeah, so project wise, items will be issued from week 2. All right, so next week, week 2, we will start the lab, but it's not a formal lab in a sense. All right, I will have another slide where I tell you what you need to do. Okay, but from now onwards, what you need to do, okay, which I also mentioned in the announcement, is to look out for some friends, all right, that you can form a team with. All right, so unlike EPP1 and EPP2, I give you the flexibility, all right, to form your own team. Okay, but your team must be within the same lab group. So if you are the 10 to 12 lab group, you must form team only within the group. Similarly, if you're 2 to 4, you form team within that group. All right, so that is something that you can probably start to look out for. All right, and basically in terms of the OS, we are going to be introducing you to this OS called the RTOS RTX. All right, which is also a very high-end RTOS environment, all right, which is a very good platform for you to start learning how to integrate RTOS onto embedded platforms. Okay, so let me just show you this video. Okay, maybe some of you already watched it. Okay, from your seniors. All right, so this is also one of the deliverables for the project. Okay, so let me bring up the video. Give me a minute here. Okay, so I hope you enjoyed that video. All right. So again, that is one of the deliverables of the project, okay, which I will show you in a while. So again, this course is a mixed course, I would say. All right. In fact, I want to do a name change some time back. We just haven't formalized it yet. All right. So I wanted to change something like embedded real-time system or something like that. Okay, but so it's still called real-time operating systems. Okay, but again, as CEG students, you need to understand and appreciate the application of this in a real-world scenario on embedded platforms. All right, so that is where this mixture comes in. So we are going to be going in depth into some embedded concepts as well, and then how RTOS can actually be integrated on an embedded platform to fulfill some requirements. All right, so that is where the project comes in. So by doing this project, actually you will learn a lot. All right, by having a real world problem to solve. All right, how do you create this multitasking architecture? How do you share data? How do you pass information from one task to another task and things like that? So all these are things you will learn, all right, and you get to apply them through the project as well. Okay, so it sort of prepares you well, okay, for future courses and projects on real-time embedded systems in the future. So in terms of learning material, okay, I have two websites. Again, still work in progress. This has a collection of a lot of the videos that from the previous classes. But again, for our classes, every week I'll also release the videos for you all to have a look. In terms of for embedded systems, I've started another website, but it's still still very early stage, so still needs more updating to be done. Okay, so I have my YouTube channel where I also upload all these class videos as well as other additional videos relating to things that I'm interested in. All right, so whenever I upload our class videos, I will send you all the Zoom link, all right, for the recording as well as the YouTube link, so you can choose to watch either one. All right, so some motivation as to why all this is really important. All right, so for example, okay, everywhere all over the world we are moving towards electric vehicles, correct? And I think many countries have set a deadline, correct, there where they are going to 100% switch to electric vehicles, all right, which is a big thing, okay, which is a very big thing. And when you talk about electric vehicles, you're talking about automotive embedded systems, real-time systems. So there's there's going to be a huge demand for computer engineers like yourself in this industry, right, to be able to support so many companies transitioning to this electric car vision, all right, and energy, all right. So in the news sometime back last year, okay, that Singapore has this massive floating solar farm, all right, that is supporting our electricity requirements. Again, this is just first, correct? So once this is successful as it is, there's a high chance that there'll be more similar ventures in Singapore, in other countries. So there's also a huge demand for engineers, all right, who can interface with hardware, develop real-time systems and embedded software, all right, for these kind of applications. Okay, another more futuristic one is probably the one from Tesla, the Neuralink, all right, where we're talking about brain-inspired healthcare or treatment or things like that. Okay, but all of this again is highly complex domains, correct? So you have AI, you have data analytics, you have engineering, you have computing, you have embedded systems. So you have a wide variety of disciplines that are needed to develop these kind of solutions, okay, and bring them to market. So there's always a huge demand for engineers like yourself, all right, who have this kind of domain expertise and knowledge. All right, so further motivation, this is something that I just showed my EPP2 class yesterday, all right. So this is a posting that just came out, I think this week or last week, okay, for Tesla. Okay, so if you want to be an embedded firmware engineer for Tesla, all right, so what do you need? Okay, let's look at the requirements. You need a bachelor's degree in computer engineering. See, all of you will qualify very soon. You need 3+ years experience in embedded hardware, which is you have, okay, while you are already a student here. All right, so this is where, for example, do you think as a fresh graduate you can apply? Yes, you can. Okay, whereas the 3+ years experience comes in because you need to be involved in internships. your own projects, all right, whatever that you do, that you keep updating your LinkedIn, your GitHub, and so on. All right, so you need to keep your profile very updated of all the things you have done. All right, so that shows your experience. All right, in such systems, like when you work on this module, that is also experience. When you do your capstone project, that is also a very extensive experience. All right. Solid background in embedded firmware systems, all right, which is what we are doing today. I mean, this module and developing in C, okay, which is what this module is about. Experience in RTOS, so that's exactly what we are doing in this module. Okay, experience in interfacing actuators, motors, vision elements, which is also what we have, correct, and to be able to deliver high quality code. Well, see, not bad. You know, you do this module, you basically qualify immediately to be an embedded firmware engineer. All right, so maybe you can try to be an intern there, you know, maybe in the next summer break, all right, with your experience that you get. All right, so again, this is in California, okay, so maybe you get a chance, you know, let me know. This is another one that also came up that I saw yesterday, firmware engineer for autopilot. All right, so if you look at all these requirements, all right, very similar, bachelor's in computer engineering, and experience in embedded development, robotics, real-time control, proficient in C, okay, understanding microprocessor architecture, and so on. Okay, I experience debugging embedded system using scopes, logic analyzers, debuggers. All right, so again, this module, okay, thankfully, all right, we are using it using the DSA lab. All right, so the DSA lab is a wonderful place, all right, with all the facilities, all right, especially the scope, the meters, and so on. Try to get more confidence in dealing with them. All right, what I've observed even in EPP1, EPP2 is there are still many of you who are still, I would say, uncomfortable in dealing with the scope, not sure what to do. Every time press the auto button and hope the magic works. All right, sometimes it works, sometimes it doesn't. All right, so try to be more confident, play around with it, you know, try to see what I can do, how I can tune the scope to get the exact measurement that I want, the readings that I want. All right, so all this will help you. All right, all this will help you to build up your profile. All right, so when you want to go join as an intern or apply for a job, you have that confidence to say that you know how to do all this stuff. Okay, so I hope this is again good enough motivation to want to learn, okay, and do well in this module. All right, so let's do a quick poll. All right, so can you all just bring out your handphone and go to this link over here, pollev.com/rsnus, okay, to do a quick poll over here. Okay, so this is just to get a view of your C programming confidence level. All right, so the C programming that is required is of course not the very tricky or type that you probably came across when you did CS1010 or anything like that. Okay, so this is more, I would say, straightforward. All right, as long as you know what you want to do. All right, you want to write a software to do write a loop to control the motors, control the LEDs, you know, perform some data processing, things like that. So as long as you are confident at a very basic level, I think you are good to go. All right. So it's nothing that where it is too advanced and you can't manage it or anything like that. All right. So as long as you have the basic stuff, I think you can easily do this module. All right. Probably the only part that you still need to maybe brush up is the extension of EP2, where we talk about all those bitwise operations, some macros, some bit shifting, and things like that. Right. So those are the parts where you probably need to just read up and just refresh your concepts. Okay, so let's look at this hardware development. So when we talk about hardware development, we're talking about soldering, breadboarding, and things like this, things like that. Okay, so you can just be honest. We're not tracking any names here. Okay, so more than half of you are roughly about okay, which is I think good. So in terms of hardware, basically what you need in this module, I think from the video you can see there's a lot of sort of getting hands dirty. All right, you need to put things together. You need to do some soldering, breadboarding, and things like that. All right, so that part I think everybody should get involved. All right, and try to do it. Okay, don't leave it to one person in the team that who will be very good at it. All right, but that should not be the excuse for you not to try. All right, I think everybody should have a go at it to try and fix up some things just to see and make sure it works. All right, so if you're not so confident, start out with something simple, maybe putting up the LEDs or the switches or something like that, you know, and then maybe soldering on the board and so on. You can leave it to somebody in the team who is maybe more experienced. All right, those who only use high power before, please, okay, hope you go beyond the high power, okay, and start to do something. All right, again, it is for your own good. All right, so for your own good to just have some exposure in doing this. Okay, even though we did try to introduce you to it in EPP2, okay, and this module also tries to do it. Again, we can't force everybody to sit down and do soldering. Correct, so it's still a choice, but I would say it's a good choice, okay, if you go ahead to try it. Okay, again, if you're not good, okay, if you think my soldering is bad, I don't want to spoil the board, all right, then no problem, you can just ask Uncle Jalil, can I have a spare board, you know, a spare, just a simple bureau board, and just put some resistors and practice some soldering and things like that. All right, so there's always ample opportunity for you to practice, make mistakes and learn. All right, so that is what school is for. All right, so you learn, and as you get better and better, then by the time you graduate, you got a lot more confidence. Okay, so what do you hope to learn from this module? Okay, so I've shared with you my vision, okay, what the scope is. Okay, so I would like to hear from you. Okay, sorry about that. Okay, OS concepts, operating systems, advanced microcontrollers. Okay, so it's good. All right. So I think generally, as long as you have the right mindset, I think you will enjoy this module. Okay. Like I said, this module is guaranteed to be fun. All right. Though there are a lot of things to learn along the way, but it's going to be a fun module. Okay, especially the project. All right. Again, the project is fun as long as you do it consistently. Okay. The point where it gets beyond fun, okay, and then you start to get a bit stressed is when you feel that you're not keeping up with the schedule. All right, so as long as you follow the schedule, okay, so if this week is supposed to do this, okay, you work on getting it done, okay, then the next week the next objective and so on. So as long as you keep up with it, I think you should be fine. And since you're going to be working on it in teams, all right, I think it's a lot better, so you can help each other. But at the same time, if you are not so strong in it, don't just rely on your friend to carry the weight. Okay, you still need to contribute, correct, in one way or another, and learn what's going on. Okay, so so let me go on to the project specifications first before we go on to the next chapter. Okay, so this project specification document is also something that I have uploaded. Again, this may be updated along the way. That's why I always put the date. This was last updated at the beginning of the year. All right, so along the way, if I feel that there is further updates that need to be done, okay, I will do it. Okay, so the aim of the project is again just to add some excitement to the module, okay, to develop RTOS-based system. And what you will be doing, as you saw from the video, is you will actually be controlling a robotic vehicle to complete a maze. Okay, how do you control it? You will use it. You will be developing an Android app. All right, so I will share with you how to create an Android app. So you'll be using what we call the MIT App Inventor platform. All right, it is a free, easy block-based app development tool. All right, so you don't need any app development experience to do this. All right, And this is also optional because you don't actually need an Android app. You can create a web app to do it as well. Okay, because we in the past we stuck with Android app because we had a Bluetooth module, all right, but the Bluetooth module was always a bit unreliable, all right, from the feedback that we got. So I changed it to a different Wi-Fi module. And with that, you now have a flexibility to not do an Android app, but you can just create a web app. Okay, you can do basic HTML coding and create a web app as well, and it will work this as well. All right. So I'll talk about that. Okay, when the time comes. Each team is given a budget of $40 for purchases. Okay, that you will incur along the way. Okay, everything that you need is given. All right. This $40 is for the additional sensor that you may need to buy, and maybe batteries that you want to top up and so on. Okay. So I'll not go through these requirements and also much. All right. So these are just requirements for you to ensure the robot is functioning. All right, and you're able to control the robot correctly. Okay. So these are some guidelines on the RTOS, which again we will come back to this. Okay, at a later time. Okay. Then you have a video submission as well. Like I said, you need to submit it to the folder at the end of the module. All right. Again, this is the grading criteria. Okay. So there will be two challenges that the robot needs to fulfill. Okay. So in the video, what you saw was the challenge run 1, which is the going around the table, through up and down the ramp, through the cones and things like that. So that is challenge run 1. All right, which is basically what I've drawn here. So we will start from the office outside Uncle Jalil there, all right, where the 2 tables are placed. Okay, and from there we will go straight. There will be a ramp, then you go around and through the cones, and then another ramp, and you come back. Okay, so that is the what you call the remote control mode of your challenge. All right, so that is challenge run 1. Now challenge run 2, okay, is the one that usually is more challenging one, because it is what you call a self-driving mode. Okay, so in self-driving mode, okay, you must be able to go. You just press a start button on your robot or your app. It goes straight. It detects an obstacle, goes around, and it comes back. Okay. So again, these are the things you need to take note of. Okay, so I will be updating this document to better show you the obstacle, how to create it, and how to build it, and so on. Okay, so I'll talk about it again in probably the next lecture. All right, but this is the challenge run 2 in self-driving mode. All right, so this is, in fact, I would say more challenging. In the past, I think there are always a few teams that give up and just say, I don't want to take this challenge because I can't get it to work. All right, and even those who get it to work, most of the time got a lot of problems where the robot will go around and then not come back, or will just bang through the obstacle without even making a U-turn. All right, so challenge run 2, even though it looks very simple, is actually a lot more challenging, all right, than challenge run 1. Challenge run 1 is easy because you have full control of the robot. Okay, so that sort of gives you a rough idea of the challenge. Okay, this is the grading criteria. Okay, so for both challenge runs, you are given first 2 attempts. Okay, for the first 2 attempts, we will take the final timing based on whether you hit the cone, whether you fall off the ramp, or things like that. All right, so we have a scoring mechanism, and then based on that, you have a final timing. Now, what happens if the first 2 runs you are still not happy? All right, you think that your robot can do better. All right, you are allowed another 3rd run or 4th run, but to be fair, the 3rd run or 4th run already has a additional penalty timing added. All right, so this is the grading criteria. Okay, so why did I add this run 3 and run 4? Okay, because in the past we only had attempt 1 and attempt 2. All right, and what happened was, especially for challenge run, either of it, you are supposed to take both the runs one after another, correct? And then after the 2 runs, the team will come and tell me that oh, they realized that one of the wire came off, or the sensor was slightly tilted to the left or to the right, and that's why the whole thing didn't work. And they want another attempt, correct? So to make it easier and to make it fair, all right, If you still want additional attempt, we have 2 more additional attempts, but each of these attempts already have a preset penalty. So whatever timing you get, you already have a added penalty to that score. So we will still allow you to take that run, okay, with this added penalty. All right, so this is to make it fair that you make sure that everything is good for the first 2 runs. All right, then hopefully you don't have to go for run 3 and run 4. Okay, so that is the product specification. Okay, just to give you an idea of what you need to be able to fulfill and complete. All right, so let me come back here. Okay, so that sort of wraps up this. Yeah. Okay, so maybe what we can do is we can go for a short break now. Okay, now it's about 10:45. So let's just take a short 5 minutes break. Okay, again, we are not going to do heavy technical stuff for today's class, just to give you some basic idea only. So let's take a short 5 minutes break. Now it's 10:47. Okay, about 10:55 we come back. Okay, and let me start on the lecture 1 to get introduced to embedded system concepts. All right, and after that we will talk a bit more on the project and the project grouping. Okay, and what you need to do for this 2 weeks before you come for the first lab. Okay, next week. Okay, so let's take a short break. I'll see you back here at 10:55, about 7 minutes time. Okay, thank you. Okay, so in the meanwhile, you have questions, you can put it in the chat. Okay, when I come back, I will address those questions. Okay, so yeah, I just want to cover this chapter for today. Okay, then the next chapter 2 we will start from next week. All right, so in this chapter, we're just going to have a quick recap of embedded systems design. Okay, what it is. All right, again, it very much relates to things you have done in EPP2. All right, so I think it's quite easily relatable. So when you talk about embedded system, in general, we say it is an application specific system. All right, so you want to fulfill some particular task. All right, so a simple, for example, aircon remote control, or TV remote control, these are very simple embedded devices. A GPS system, okay, MP3 player, these are also embedded systems. All right, so generally we say that these systems run with the idea of having low cost with more features. All right, at the same time you want to have some good performance, all right, and dependability. And to make all of this work, you generally use microcontrollers, or what we call embedded computers. All right, and those readily available ones are what we call the high volume ones, so the recurring cost is low. So you take some off-the-shelf microcontrollers, all right, and you can straight away use that in the application. So just like how you use Arduino Uno in the past, we're going to be using the Freedom board, all right, in this particular module. All right. So of course, you can also have more complex embedded networks where you have different devices talking to each other across a network. Okay. Now, in terms of building embedded systems, all right, what are the common approaches are generally microprocessor and microcontroller. Okay, so the microcontroller approach is like what I said, you use a readily available board, all right, with a microcontroller chip on board, and you start to do the programming and hardware integration and things like that. Now, the other alternative is you can build your own board using a microprocessor with memory and systems and so on. This is of course more challenging, all right, but it gives you more flexibility, all right, to customize to the exact needs that you want. Okay, but I would say the flexibility also comes with microcontrollers, because most microcontrollers, when manufacturers release them into the market, they already come with some variation, right? So the same microcontroller board, all right, may come with maybe one version which is 64 kilobyte memory, another version which is 128 kilobyte memory, and so on. So they already come with some different flexible options, all right. But again, if you want to really customize it to something that you want, then you can use a microprocessor and go ahead and do it. Okay. The other option is what we call using FPGA, okay, which you'll learn in I think one of the elective modules. All right. So the FPGA is basically hardware description language, HDL. All right, Verilog or VHDL. Okay, so that is a way of programming, writing software that get translated to hardware. All right, so that is a whole different uh, area by itself. All right, but that is of course very, very good because it allows true parallel processing of information. All right, but again, that is quite complex, and you really need people who are proficient in HDL programming to work on the project. All right, whereas if you take these two options, you're generally talking about C development, so you have a wider pool of people who can tap on. All right. The other one is of course from FPGA, you can go ahead to make a custom ASIC. All right. If you make a custom ASIC, again, your the advantage is you can reduce the overall cost. All right, but that only makes sense if you have very, very high volume, okay, millions of products. Then I would say it is worth the money. All right, if not, the amount of money you will spend into customizing and sort of creating your own ASIC may not be something you can get as a return. So these are the general trends and options available for building embedded systems. All right, so our focus is generally in the area of microcontrollers and microprocessors. Now, let's look at a very simple system like this, where you have a bike performance tracker. Okay, so of course nowadays I think most of them straight away can integrate with the app. So your handphone app will just integrate with the sensor on your bike, and you can do this performance tracking. But let's say you just want to go to something very, very basic. Okay, so a device like this, okay, where you have sensor integrated, all right, to capture the wheel rotation. Then you have a simple input, which is a button press. So what do you want to do? You want to measure speed and distance, all right, but at the same time, you want it to be small in size, low in cost, battery must last long, and so on. So looking at these requirements, you can easily say that you need something that is a very simple, low performance microcontroller. All right, so something like what we use, the Arduino Uno 8MEGA328 is more than enough to have to fulfill the requirements of this. All right. How about something that is more complex, like a gasoline, automobile, ECU, engine control unit? So an engine control unit has to do a lot of work, okay, because it has to take in inputs from so many different sensors and signals, correct? At the same time, process all of this information and provide the necessary outputs, okay, for the injectors, the ignition, okay, to drive some bridges, the outputs. So you can see that at any point of time, it has a tremendous amount of work to do. All right, dealing with so many inputs, so many outputs, okay, and everything has to be done in real time. All right, you cannot have an ECU that is going to be lagging or is not going to be able to keep up with the requirements, all right, because lives are at stake, correct? When a person gets into the car, they expect that the ECU is working correctly, so that when they drive, they press the brake, the car must be able to stop. Okay, you cannot have a situation where you press the brake and the car tells you, oh, sorry, I'm changing the music right now, I will brake a bit later. No, it should not work that way, correct? So you should have a sense of priority among all the different tasks, the different interrupts, and so on. Okay, so looking at such a high performance system, you definitely need an equivalently power or high performance microcontroller, okay, with the efficient memory and speed, processing speed that you want. All right, so this is also a good time for you to look into what is MISRA. So if you do not know what is MISRA, you can go and Google it. All right, so this is just something for your knowledge. Okay, so this is a programming standard for those who wish to enter the automobile industry. All right, so even though we have C as a standard, all right, there are some things that are guidelines where some things are allowed and not allowed when it comes to writing software, for example, for automobile applications. So MISRA is a body that is a sort of standard that tells us these guidelines, okay, what is allowed and not allowed when you're writing software for these applications. All right, so the whole idea is, of course, you want to make embedded systems to be as efficient as possible. All right, so on one side, you have the hardware, the other side, you have the software. All right, so the software allows us to make full use of the hardware, okay, and write very complex algorithms and things like that, to to achieve the control that we want. All right, so of course, these are just different type of examples. I'll not go through. Okay, so a closed loop system, okay, sequencing, signal processing, communication. These are all the various functionalities of embedded systems. Okay, so again, this is just general stuff. Okay, and at the same time, we want to be able to also interface with larger systems. All right, so you may have multiple embedded devices that can be interfaced together for a greater, higher level objective. So similar to the automobile example here, okay, each of these sensors that you see here may already be interfaced to its own microcontroller that is processing the actual analog signal and providing a digital output. All right, so there could be many microcontrollers in all these subsystems that process the first level of information and send this data to a higher level microcontroller unit that eventually does some higher level decision making. You know, so that is what we're talking about here. Now let's look at a simple example. So if I say I have this analog sensor, a pressure sensor, and I want to take this reading from the pressure sensor and sort of do some calculations with it to get the actual pressure information, the depth information, and so on. Okay, so what I can do is I can always take the sensor reading, okay, and perform an A to D conversion. So when I do the A to D conversion, of course, I need to relate it back to the actual values. All right, so the A to D value gives me the conversion of the analog to the digital, but that value still needs to be related back to the actual pressure. All right, so the output must relate back to the pressure. So that is where a graph like this, the relationship graph, gives us an easy way of referencing. Now, this is of course a very simple relationship, is a straight line. All right, so with a straight line relationship, it's easy to come up with a straight line equation and relate the input and the output together. So once I get the pressure value, okay, also the output value in terms of the voltage, I can relate it back to the pressure. Okay, so any relationship is easy to define. Okay, now just for discussion, let's assume that this graph is not so nice. Okay, so imagine that instead of having it as a straight line, okay, the graph looks something like this. Okay, where this is the voltage and this is the pressure. Now, how would you deal with something like this? Okay, so this is of course more complex. Yeah, so you can do piecewise, correct, and then you can also consider lookup table, correct. Yeah, so these are two possible ways. So piecewise means you take this graph that you have and you break it up into specific sections, and then you try to see which section it can map to. Okay, the other one is of course you can always do a lookup table to say that, okay, if I'm in this region of the lookup table, then this is the pressure and so on. Okay, so it is not so easy. All right, so you need to think of which solution fits your application best. All right, and of course in some cases maybe you don't need to even worry about the whole graph. Okay, maybe the pressure you're trying to measure, okay, is only in the region of maybe, for example, 200 to 250. So I only need to worry about maybe this particular voltage range. All right, so sometimes you can simplify the problem by narrowing down to what you're really interested in. All right, instead of trying to come up with a solution that can fit a wider scope. All right, so again, all these are what you call engineering solutions. Right, so theoretically you have all of these constraints. So when you try to come up with an engineering solution, you try to see what is the easiest and most effective way to solve the problem. All right, so that is what engineers do. Right? We try to solve the problem and we try to solve it correctly, but at the same time, if there are some assumptions that we can make, okay, that can simplify the problem, then we make those assumptions and then we go ahead to solve it. Okay, so again, this is a common I think misconception among many people. What is a microcontroller? What is a microprocessor? So to put it simply, a microprocessor, okay, is basically the core of the processing system. Okay, that means that is the one that does the three most important things, which is the FDE: fetch, decode, and execute. That means I fetch the instruction, I decode the instruction, and execute the instruction. Okay, so the workhorse, all right, the one that deals with all the execution of the instruction is what the microprocessor is there for. All right, but of course, for a microprocessor to work, you need some very basic fundamentals, which is the interconnection, which we call the bus. Right, so you have the address bus, okay, data bus, and control bus. Okay, so this will of course interface the processor to some basic memory and basic I/O. Now, a microcontroller is where you have all of this plus everything else in terms of the peripheral subsystems. So things like analog interfacing, timers, communication, okay, GPIOs, and so on. So when everything comes together, all right, into a single chip solution, that is what we call the microcontroller. All right, so the Arduino Uno, the AT328P, okay, the ARM Cortex, the KL25Z microcontroller that we're using, all of them are microcontrollers. Why? Because they are a single chip solution where everything is built in. All right, so it's easy for me to just take that chip, plug it anywhere, and straight away I have PWM, I have UART, I have I2C, I have everything. All right. Whereas if I just take a microprocessor, it's still the bare minimum. Okay, I can still run code, I can execute code, but all these peripheral subsystems I will now need to build up and interface myself. So that is the main difference. Okay, so in terms of embedded systems, of course, we want the system to be able to be handle real-time responses. Okay, so everything that we want is in a way real-time, correct? Whenever we take any device, correct? So if I take a TV remote, okay, if I press the on button, I expect it to switch on the TV, correct? So there is always some real-time expectation that is there. It's just a matter of whether those deadlines are considered to be hard deadlines or soft deadlines. All right. So if I press the button and the TV doesn't switch on, or it switches on maybe 2 seconds later, it is still fine. Okay. So sometimes maybe 1 second later it switches on, sometimes 2 seconds later it switches on. All right. But either way, it is fine. The TV will switch on and everybody is happy. All right. But so in those cases, we say this is a soft deadline. Okay. So I just need to make sure I do it, but maybe it's a bit delayed once a while, it's fine. But in a system where timing is important, like for example, engine control unit, correct? When you press the brakes, brake pedal, the brakes must activate, correct? Within maybe a certain 1 millisecond or 500 microsecond or something. Okay? So whatever deadline that is set by the manufacturer, the brakes must activate and stop the car. Okay, you cannot have a delay in that. Okay, you cannot allow room for error in that. Okay, so in some cases, you must meet the deadline. So that is where the concept of real time comes in as being more important. All right. Now, how do we achieve this concurrency and real time in the current environment? All right. So if you look back at EPP2, we have introduced you to the concept of interrupt. So this interrupt is basically a way for me to achieve concurrency, okay, and also some real-time response. Okay, so how does it work? That means when I look at this example, so I can have a main software, all right, that is running. Okay, so periodically I say I start the timer, and then I can have a timer interrupt. So this timer interrupt is a hardware trigger interrupt. Okay, so my timer block generates some interrupt every maybe 1 second or so on. So every time it generates an interrupt 1 second, okay, I will jump to the interrupt service routine. And inside the interrupt service routine, I can now schedule other tasks. Correct. So I can maybe start the A to D module, and A to D module can once started, it may maybe trigger. Okay, so after it triggers 4 times, okay, and I capture some results, I can deactivate the ADC interrupt, all right, and set the flag. All right, and then wait for the next timer interrupt to happen. So what does this tell us? That means during this time over here, Okay, from the first start timer to the next start timer, my main loop can be doing other things. Alright, I can have other things going on over here, while in the back end, based on the timing that I have set aside, the interrupts will trigger, the ADC will trigger, and I'll be able to capture the response as well. All right, so we already have this idea of concurrency in real time, even without learning operating systems. Correct. And before we even start operating systems, with the microcontroller and its hardware alone, we are already able to achieve concurrency and achieve some level of real-time response. All right, so it is good. Okay, we already have this. Okay, but of course, it is not sufficient in a sense that you are still limited to hardware-driven peripherals, and there's also a limit to how much hardware you have. Correct. So any embedded controller you take, you only have a limited amount of timers, limited amount of ADC, and so on. So though it is good for many basic applications, once it becomes more complex, okay, it is a challenge to handle the real-time response and the requirements. All right, so beyond real-time, you also need to be able to do some fault handling, and you also need to be able to do some diagnostics. Okay, so these are things that are not so covered in detail in this module, okay, probably in other modules. Okay, so these are again some of the constraints that generally have in most embedded devices. Okay, so just about any device you buy, okay, if you go, I mean, nobody looks at the user manual nowadays, all right, but if you do look at the user manual, okay, they will always talk about things like what kind of charger you should use, because many of times I think we just mix and match chargers, all right, based on convenience, but they always have a specification. They will always also specify the environment, all right, exactly what is the temperature range in which these devices can be used. All right, so again, these are important, okay, for you, because maybe when you are having your own startup, you're creating a product, okay, can your product work reliably well in a country where it is very hot or it's very cold? You know, will it run into issues? So these are things that you may also need to consider when you're building your own product. All right, again, these are the other constraints, like I said, memory, all right, which you need to take note of, and all the other peripherals that you are going to interface with. All right, so in terms of programming language, okay, I would say that until now, C is still the preferred choice for embedded systems across the board. All right, so even though we have Python that has been quite popular, and there are still Python-based compilers for microcontrollers available, the general industry trend is still to use C, okay, because it is the support is still very strong for it, okay, because it very closely matches the hardware that we are dealing with. All right, and in terms of operating system, we will cover that, all right, in this module to understand how the OS can be integrated to achieve the real-time response that we want. Okay, so as a question, how does on-chip RAM, ROM reduce circuit board complexity and cost? All right, so again, it ties down to, like I said, when you say on-chip RAM means the microcontroller already has built-in ROM and RAM. Okay, so what happens is if I use this board, I use this microcontroller, but along the way I realize I don't have enough ROM and enough RAM, then you are stuck. Correct. So you only have two options. Either I change my controller, or I extend my board. Okay, so I use my address bus, data bus, control bus to add on more memory. So if I add on more memory, then my circuit board, the overall circuit board will now have to accommodate these additional chips, correct, which also means my cost goes up. All right, so that is where again, this is a very common issue that I've seen come across by students who do projects, where they start off with a particular board, all right, because they are familiar with it, all right, but along the way they realize that they don't have enough of what they need, either it's memory or peripherals or something like that, all right, and then they're stuck in this situation. Do I change my controller, or do I add on to my current board, you know, and add the peripherals there? All right, so again, this is an issue that can be prevented if you think ahead of all the requirements and try to to choose the most optimal board that you want. Yeah, so basically what that line says is that if you add on the availability of on-chip ROM and RAM reduce the circuit board complexity and cost. So if the on-chip RAM and ROM is not enough, then you add on these additional ones, then you will have to increase the circuit board complexity and the cost. Okay, so that is what that line is saying. Okay, so let's come to the board that we are going to be using. So this is the 32-bit Cortex M0 Plus processor core board. All right, so the Cortex M0 Plus is basically the ARM core. Okay, so again, why I chose this is because ARM is of course the #1 processing core in the world right now. All right, almost all smartphones in the world, majority of them are powered by ARM. All right, it's also coming into the desktop space, the laptop space, and so on. So I think to have exposure to this, I think is good for your profile, for your resume. All right, so this is the processor core, right? So of course we're not going to go into the internals of ARM assembly language programming and the register level interface and things like that. Okay, so those are things I think you will learn in another module. All right, so we are more interested in using the processor as a microcontroller together with the peripherals that we have. All right, so generally I will refer to this as the Freedom board or the KL25Z board. All right, so this board is again comes with a whole host of features, all right, which we will explore some along the way. All right, in terms of the platform, all right, the Lab 1 manual is already released, okay, with the microcontroller software folder, okay, in the Luminous. So you can go ahead to install the necessary software, all right, and get everything set up. All right, so this board also can be is compatible with this platform called OS Embed. So let me just show it to you over here. Okay, this here. Okay, so as you can see here, this is the KL25Z board on the OS embed. So this OS embed is embed is a OS created by ARM to support their microcontrollers. All right, and so initially I was thinking of using this. Okay, this was a few years back. All right, but I went with the RTX option. Again, why? Because if you look at the, for example, sample code, all right. So let me just show you why. So this is the Blinky code. Let me show you here. Yeah. So if you look at the code, what do you see? You see that it is very much like how you were dealing with when you were doing your sketch programming. All right. So you really wouldn't learn anything significant if we stuck with this OS embed interface over here. All right, so again, this is their way of making it easy for people to come on board and learn about their boards, learn about OS and things like that. All right, but I think as a computer engineer, you need to learn it at a much more deeper level. Right, so that is where we are using the board, but we're not using the OS embed platform. All right. But you are free to, of course, use this in your own time, right, after the module is over. All right. The advantage of this ARM embed is it actually has is a fully online compiler. All right, which means that you don't need to actually download anything. You can run your code, compile your code, everything, and download just the executable, which you can drag it over to your board. All right, and then your code will run. All right, so that is the advantage of the OS embed platform, but we are using the KL, what do you call that, the RTX platform, okay, with the KL IDE. Okay, so that sort of gives us a good introduction to the board. All right, so important admin stuff, okay, that you need to do. All right, so within your lab group, okay, within your own lab group, you need to form a project group. Okay, it must be the same group. Okay, I mean the same lab group. Okay, so as I mentioned, if you are part of the 10 a.m. slot, you must only look for members within the 10 a.m. slot. If you are the 2 p.m. lab group slot, then you only look for members within that. Okay, once you look for members, okay, you are free to choose anyone. Okay, you can register yourself in Luminous. All right, so if you go to Luminous, let me show you where. You can go to class and groups. Okay, so I already created this project group for BO1 and BO2. So you just select which group you are in. So let's say you are in a 10 a.m. group. Okay, and then all of these are open already. So you can go ahead and register under any team number. Okay, so you should only register, okay, once you have formed your team. Okay, don't go and say, oh, 7 is my lucky number. I'm Cristiano Ronaldo fan. I want to choke number 7. No, okay, so make sure you only register after you have formed your team. Okay, and then you can come in here and register whichever team number you like. Again, team numbers do not matter at all. All right, like I said, all the teams will surrender their robot at the same time. Okay, so everybody gets the same amount of time to work on the project. So it makes no difference. All right, so this is just more for admin purposes only. Okay, so that is something that you need to do. All right, so look out for your friends, okay, who are in the same project lab group, and try to register. Okay, again, choose your teammates wisely. Okay, so interestingly, there's always some issue, correct? EPP1, EPP2, you know, most students say, oh, you know, I'm not allowed to choose my friends, so I'm in a group where, you know, I can't get along with them. Then here we allow you to choose. Again, at the end, there will be complaints that, hey, my friend initially was okay, but towards the end, he stopped working. You know, so there's always issues. Okay, but again, since you're forming your own teams, you deal with, you know, the dynamics of the team. Okay, and get everybody together. Okay, of course, if it comes to a point where things are really bad, all right, where, for example, one team member is really not working, and you think you need to bring it up to me, let me know earlier. All right, and I will try to see what I can do to talk to the person in charge, involved, and resolve the issue. Okay, try not to hold it till the end of the semester and then you come and say that this person didn't do, you know, that person didn't do, and then the module is over. All right, so it's a bit more tough. So the earlier you tell me, okay, I think my objective is not to penalize you all, but to encourage you all to work together. All right, so the flexibility is you have the ability to choose your teammates, but if there are issues, then I will still be willing to come forward to mediate and try to help resolve whatever are the issues. Okay, but only if you bring it up to me earlier. Okay, now the last part. What if you don't have anyone to partner with? Okay, because some of you, I think, are from an earlier batch. Maybe you delayed the module. All right, so maybe you don't have any friends in this particular batch. All right, so no problem. If you don't have anyone to partner with, all right, I will send out a poll next week. Okay. So I'll give your time first, right? So if you still cannot find anybody, you can fill up that poll, and then what I will do is I will group you all together, okay, or I will assign you all to teams that have maybe only 3 members and make it a 4-member team. All right, so again, it all depends on the dynamics. I still remember about 2 batches ago, there were 4 students in one of the lab group that didn't have anybody to partner with. Okay, and then I just say, okay, since 4 of you don't have anybody, I'll just group you all together. So these 4 students did not know each other at all before that module. So I just randomly grouped them together, and their team robot actually came in first. Okay, for the challenge run. Okay, so I think it's just a matter of being I'll say practical about it. Just like how you go out to work, you don't get to choose who your colleagues are, who your bosses are. Okay, you focus on the work, focus on what needs to be done, then I think things will go smoothly. All right. Okay, so next Friday is we will start the lab. Like I said, it is in an unofficial lab in a sense that you don't need to do anything much, but you just need to come to the lab to collect your project kit. Project kit only for the teams that have already registered in Luminous. Okay, for the rest of you, you can come and collect the Freedom Board. Okay, so each of you will receive one Freedom Board. Okay, every student will receive one Freedom Board. Okay, please be extra careful with the board. All right, and once you collect the board, you must do lab 1. So I've already released lab 1. So what is lab 1? Lab 1 is just to make sure you unbox it. Okay, if you want to create unboxing video, please go ahead and do it and upload to YouTube. All right, but if not, you just unbox it and then you just check that everything is working and you are able to see the RGB LED working and so on. All right, so that sort of confirms that the board is fine. All right, and we just want to make sure that you confirm the board is fine before you leave the lab. All right, so next week's lab, everybody, if you don't want to come to the lab, you can ask your teammates to collect for you. All right, the KL25Z board. The project kit will be given to those teams that are already registered in Luminous. So if you still have not registered, no problem. You are not losing on anything. Okay, we are not going to be touching the project kit items until probably in week 4. All right, so you have enough time, all right, to play around and get settled with the lab. All right, so we will issue you the project kit for registered teams. The rest will get one Freedom Board each. Okay, so another important thing is this work from home lab arrangements. All right, so this is something new I just added. I will update an announcement on it. So because of the current safe management measures and we are slightly oversubscribed. Okay, we have 102 students. All right, and we are only allowed 50 at any point of time in the lab. Okay, so because of this, okay, we are unable to handle the full capacity at any point of time. So what we need to do is every team has to prepare a work from home schedule and upload it to Luminous, where you allow one team member to rotate, okay, every week to be working from home. So this working from home is not sleeping at home till 12 o'clock or whatever. You still need to wake up. You still need to log in with the Zoom session created by the lab TA. So attendance will still be taken. All right, and we will, the TA will check, okay, that the schedule is fair, that every team member is rotated fairly throughout all the weeks. So you cannot have one person say, I volunteer the whole semester work from home. No, you have to rotate among everybody. Okay, so so I will send an announcement on this later today. So those who miss it can have a look at it. Okay, so again, this one will only come to effect from week 3 onwards. Okay, from week 3 onwards. Next week, after you collect the lab from the, sorry, after you collect the board from the lab, you have tested it, you can leave. You need to stay for the full lab session. Okay, just to make sure you collect the items, okay, to prepare for lab 3, week 3's lab. Okay, so that's all I have. Okay, so the important thing, like I said, is forming your project group. Okay, so that is something that is important. Again, do not worry if you are unable to form. Like I said, those who are unable to form, I will group you all together, okay, into a project group, okay, or I'll assign you to team members that only have three members, teams that only have 3 members. Okay, so if possible, try to have groups of 4, if not form groups of 3, and then register in the Luminous. Okay, and then those who don't have anybody, I will do it for you all. Okay, so again, that's all I have for today. All right, I think the next lecture we will start next week. All right, then I will be just nice. All right, and I will talk a bit more about the board and how to handle it more safely in the next week's lecture. Okay, so that's all. If you have any questions, you can stay back and ask me. If not, I will see you all next week.